We've looked at calculating intercepts for other types of functions. Now we want to do that for rational functions. Most of the concepts are pretty much the same. We're going to add in a few extra pieces here. But x-intercepts occur at a point of the type x, comma 0, where x has some value, but y is always 0. And for any y-intercepts, we're looking for points of the form 0, comma y, meaning y takes on some value, but x is definitely 0. To find those intercepts, we set the opposite variable equal to 0 and solve from there. All of that's the same as what we've seen with previous topics, previous types of functions. But now that we're dealing with a rational function, p of x over q of x, a polynomial divided by another polynomial, we need to keep in mind that all we need to do to find intercepts, or to find x-intercepts, is just set the numerator equal to 0. We don't need to worry about setting the denominator equal to 0 as well, because a 0 in the denominator gives us a restricted value, a point where that function is undefined. So to find x-intercepts, we set the numerator equal to 0, and then separate from that, we will still set the denominator equal to 0 to determine the domain of the function. To make sure that any intercepts that we find are within the domain of the function. In order for an intercept to exist, it must be within the domain. And we'll see some examples of what we mean by that. In example 4, we're given a function. We want to find the x and y intercepts. We're not explicitly told to do this, but we're going to start with an implied step where we first find the domain of this function. So the denominator of this function cannot equal 0. Solving those two factors set equal to 0 gives us two restricted values. X cannot equal 4/3 or -5/4. As we find intercepts or potential intercepts, we just need to check them against these values. To find the x-intercepts, we set our opposite variable equal to 0. Meaning we set our function equal to 0. All we need to worry about is where the denominator is equal to 0, because 0 divided by anything would be 0, except for 0 divided by 0. So we'll take just the numerator and set that equal to 0. Setting our two factors equal to 0 gives us two solutions, x equals -5/2 and +3. Neither of those values conflict with our restricted values, meaning we have two x-intercepts, one at -5/2, comma 0, and one at 3, comma 0. To find any y-intercepts, we set the opposite variable equal to 0, so we'll plug in 0 for x. As we evaluate p of 0, in the numerator we'll get that first term in 2x plus 5 just going to 0. So this will become 0 plus 5, 0 plus 3, all over 0 minus 4 times 0 minus 5. All of the x variables go to 0, and we just look at the constants that are left over, because 0 plus 5 would be 5 times 3 over -4 times -5. We could either multiply together and reduce, or reduce first. 5 divided by -5 would reduce to 1 over -1, and we're left with 3 over -4 times -1, or 3/4. This tells us that we have a y-intercept at 0, comma 3/4. In example 5, we want to do the same thing. Start off with that implicit step where we set the denominator equal to 0 and solve, because we can't divide by 0. In this case, that leads us to a single result, which is that x cannot equal 0. And then we carry on like we did with parts A and B above. We'll start off by taking the numerator, setting that equal to 0. Here we'll take the square root of both sides, which means we have to introduce that plus or minus notation, but the square root of 0, or the opposite of the square root of 0, is just 0. So we get negative x plus 2 is equal to 0, or negative x is equal to negative 2, or x is equal to 2. In this case, we come up with a single x-intercept, which is 2, 0. 2 is not a restricted value, so we'll keep that intercept. Then we'll evaluate m of 0, meaning we're setting x equal to 0. To get 0 plus 2 squared all over 0 squared. This result doesn't exist. It's undefined, or actually more specifically 0 divided by 0 is referred to as indeterminate. But it's enough for us to know that we can't divide by 0, so this doesn't lead to a solution. We found this out, in this case algebraically, but we could also do this a little bit more intuitively. Since we know x can't equal 0, that means there are no points of the form 0, y. A point like that can't exist because x equals 0 is outside of our domain. So in this case, we would say DNE or does not exist.